Okay, so we are on chapter 1, section 4, types of functions and their rates of change. So our objectives are to identify linear functions, interpret slope as a rate of change, identify nonlinear functions, identify where a function is increasing or decreasing, use and interpret average rate of change, and calculate difference quotient. Those are our objectives for the day. Okay. Let me just slip there. So just reviewing, linear functions. Looks familiar? It should. You've been dealing with this for a while. So a linear function, a function f represented by f of x equals mx plus b, and m and b are constants. Okay, m and b have values that they represent. M can be called your slope, rate of change. Your rate, your constant rate of change. Your b is called your y-intercept, your starting point, your initial value, your constant. All those things. Our other function, another linear function, a specific one is called a constant function. A constant function has a constant value only. So it's y equals c, or f of x equals b, or it is a horizontal line. It's our constant function. So when you're recognizing a linear function, there are key things that you want to acknowledge. Is there a constant change? Is there initial start? And how is it going? So here we have a car initially located 30 miles north of Texas border, traveling north at 60 miles per hour, is represented by the function 60x, f of x equals 60x plus 30. And the reason why we know that is because it told us we have an initial and we have a constant rate that we're traveling. And therefore it can be modeled as a linear function. Okay, we have our initial, which falls on our y-axis. Here's our b. And then our constant rate of change is how much am I changing each time. So I'm here at 30, then I'm at 60, 90. So I went from 30. Pretend those are super straight lines. And now you have your constant rate of change. So it's not 30. Is it 30 to 90? Yeah. And I changed over a course of 1 hour. So I was at 30, so it's 90 minus 30 over 1 minus 0. And that's how we get our 60 miles per hour. Okay, rate of change of a linear function. That's what we just kind of did. In a linear function, each time x increases by 1 unit, the value of f of x always changes by an amount, and it's the equal amount. That's why it's slope. Your slope is your m. It has to be equal. Each time that change is the same. It's a consistent, constant rate of change. And so m is what represents that, and that is called our slope. Yay! M means slope. So here, if I was asking you to find the rate of change of the function between the times. So I'm asking you to calculate the rate of change between 0 and 1, 2 and 3. So if we were to calculate the rate of change from 0 to 1, all I'm doing, I'm saying, where did I start? So this would lead me to 90 minus 30 over 1 minus 0. That gives me 60 over 1. All right, so then I'm going to check it from 1 to 2. So what happens from 1 to 2? We're looking to see, is it a constant rate of change? So that gives me 150 minus 90 over 2 minus 1. That gives me 60 over 1. Oh, still the same. 2 to 3. I have 210 minus 150 over 3 minus 2. That gives me 60 over 1. So my constant rate of change here is 60. And when you're writing your units are your dependent per your independent. So my dependent is distance in miles per hour, because that's my independent. Sounds familiar? Slope of lines as a rate of change. So actually, what we were doing, we were looking for the constant rate of change. We were actually calculating the slope of the line. And if you remember your slope, m between 2 points, it's your change in y over your change in x. So change in y over change in x. And what that means, I have y2 minus y1. So we have y2 minus y1 divided by x2 minus x1. Because change means to subtract. You're finding the difference. And that's what this delta, I know you like, it's just a triangle, this. It's a delta in the terms of this. Delta y, delta x. And this means change, which is equivalent to subtracting. Find the difference. Okay. Graphically, what you're doing, we learned it as rise over run. Remember that guy? Rise over run. I also say fall over crawl, because sometimes it's easier to go down and then move horizontally. But it's your rise, how high did you go up, and then how wide did you go horizontally. So our types of slope, we have a positive slope. Positive slope, if the slope of a line is positive, the line rises from left to right. And so if we look here, this is a slope of 2. And it's a positive slope because it's rising from left to right. Okay, negative slope. Negative slope means the line is falling from left to right. It falls from left to right, so I'm decreasing from left to right. Example here, when the slope is negative, there is a negative value for your m. M is less than 0. So as my x increases, my y decreases. Next, we have slope of 0. We have slope of 0. And slope of 0 indicates that the line is horizontal. So you're just steady. Think about a treadmill. When you put this treadmill at 0, you're just walking straight. And then you press that incline or that decline, if you have a really fancy treadmill, that's when you're changing the slope of it. And then our slope is undefined. And that's when x1 equals x2, the line is vertical and the slope is undefined. All right, any questions so far? So we're gonna kind of put this all together. How many of you remember Slope Man? Did anyone ever see Slope Man or teacher model Slope Man? Slope Man, slope guy. He represents all the types of slopes you have. So his mouth is your constant. His nose is your undefined. His eyebrow, you have your decreasing and you have your increasing. And here is your Slope Man. Boom, Slope Man. Okay. Another way that for remembering what is horizontal and what is vertical slopes, hoy. We have hoy, vux. So in 8th grade, I started saying this, hoy vux. I called it my math cuss word. But it stands for horizontal, have 0 slope, and it goes through the y-axis. Vertical are undefined and go through the x-axis. So there'll be y equals and x equal, but oi vux. Remember when you were in 8th grade and everything was so lame and cheesy. But yeah, so just some little tidbits on slope. So if we're calculating the slope here, and I ask you to find the slope between these 2 points, you should feel pretty comfortable, I assume. I'm going to model one. So we have our x1, our y1, our x2, our y2. And remember, slope equals y2 minus y1 over x2 minus x1. So that's going to give me 2 minus 3 over 1 minus negative 2. Oh, it's negative 2, that's right. And so negative 2 minus negative 3 is negative 5. A negative times a negative is a positive. So 1 plus 2 is 3. So my slope would be negative 5/3. So because I have a negative 5/3, what does that tell me about my line? Chime in either through chat or verbally tell me what that means. So if I have a slope of negative 5/3, what does that mean about my line? Anyone? Okay, it means that my line is decreasing. So this is because I have a negative slope. The line decreases from left to right. All right. Okay. So if it asks you for the zero of a function, the zero of the function is AKA your y-intercept, which is AKA your b constant. Okay. When you're finding the zero of the function, all that is saying is that you have f of c equals 0. What number will I plug in for x that will give me the value of 0? That's all it's asking, the zero of the function. And the reason why it's just 0, just 1 0, is because you only can have one y-intercept in a function. If you have two y-intercepts, then it's not a function. All right, so looking at slope from all representations. So if you have verbal, you're describing it as your constant, or you're saying you're multiplying the input by 3/2 and adding 3. So you can identify your slope and your y-intercept from there symbolically. So you have your symbolic representation. So symbolically, you're writing it as an equation or a function or an equation. And then numerically is your table, looking at the table and finding the difference from one value to the next, and then dividing. And then graphically, if we're finding slope or y-intercept graphically, to find the y-intercept, we go to the y-axis. And to find the slope, that's when we do rise over run. All right, here is your student practice. So I'm going to pause and give you a moment just to make sure you're comfortable finding the slope, the y-intercept, x-intercept, and writing. Well, I gave you the graph. You have to do it now. All right, so let's go over this quickly. This is a pretty simple one to go through, just to make sure that you understood the concept is what we're doing here. So the slope, if I was to look at the equation, my slope, because there's no coefficient in front of the x, m equals 1. Your y-intercept, when you're writing out y and x-intercepts, that means you're writing them as ordered pairs, okay? Your y-intercept is going to be your 0, y value. Your x-intercept is going to be x, 0, right? So when I look at this graph, my y-intercept is at 0, -1. And my x-intercept is at 1, 0. When it's asking for any zeros, your zeros are saying, where do you have 0 value at? You're just saying at x equals 1, that's a 0. Y equals 0, and at x equals 0, you have y equals -1. Depending on the problem, it'll be more specific. If it's asking for the 0, that's your y-intercept. If it's asking for any zeros, that's when you're identifying your x-intercepts. The difference between zeros and intercepts is zeros is you're saying where they're located. X-intercept is writing it as an ordered pair. It's just same thing, just asking. A quick review of nonlinear functions. So if a function is not linear, then it is called nonlinear. And so the characteristics of nonlinear functions, the graph is not a straight line, thing number one, does not have a constant rate of change, and it cannot be written in slope-intercept form, and it can have many numbers of zeros. So that means it has multiple x-intercepts, or can have multiple x-intercepts. So the ones you should be familiar with, we have square root function and the quadratic function. I don't know why. I think they just wrote square so you can see the fact that it's square root, but remember this is just your quadratic function. And neither one of these are linear because they have none of the linear characteristics. And if we were to find their rate of change, it's not called constant, it's actually called average rate of change, which we'll get to later. Here are two other common nonlinear functions. We have our cube function, our cubic function, and our absolute value function. The absolute value function is actually linear functions and using piecewise, but as a whole, it is not linear. Right? The graph is uphill, you're moving upwards, right? Makes sense? When you are decreasing, you're moving from left to right, and you're going downhill. A graph can be made up of downhills and uphills. And so this is an example of a decrease, then an increase. Okay? When we're writing increasing and decreasing on intervals, we want to write them using parentheses. You don't use brackets, you're using parentheses because you're not defining the value. You're just saying it's happening from here to here. Okay? So for example, when I look at this graph for a constant means I'm staying the same, I'm not changing. So my constant took place right here in the green from 2 to 3. Increasing, I'm increasing on a couple intervals. So I'm increasing in the red from -4 to -2. And I'm also increasing on the red from 3 to 4. And then decreasing, even though it's different slopes for the decreasing, this whole thing is decreasing. So I'm decreasing from -2 to +2. Notice how my intervals are only defined by the x values. At no point do I identify what the y values are. It is strictly defined by my x values. Over here, when we look, notice that this graph goes on forever. So when I'm writing increasing and decreasing on the interval, so it's decreasing. So my decreasing is going to be from -infinity up until 0, because that's where I stop decreasing. And then from 0, I start increasing. 0 to +infinity. Any questions on increasing and decreasing on the intervals? Okay, so here, suppose that the function f, this is just a very formal definition. F is increasing on the interval if whenever my x1 is less than my x2, f of x1 is also less than f of x2. So what this is saying is if you have an interval, let's say my interval is from 1 to 2, and I tell you the values of f of 1 equals 3 and f of 2 equals 5. When I'm comparing my x's, so when I'm comparing 1 and 2, 1 will be less than 2, check, and then 3 will be less than 5, check. So this is an increasing interval. Okay, f decreases if on the interval, whenever x1 is less than x2, your f of x1 is greater than your f of x2. So if I'm still in that same interval, from 1 to 2. But this time, f of 1 equals 5, and f of 2 equals 3. This time, my x's are fine, but my f of 1x is greater than my f of 2x, and therefore this is a decrease. Okay, so here's our example that we're going to do together. We have the graph of f of x equals 4x minus 1/3 x cubed. Okay, so it's asking for intervals of increasing and decreasing. I'm going to go through, I like to identify them first and then go from there. I'm going to do my decreasings in yellow. So I'm decreasing, and I am decreasing. I'm going to do my increases in red, and here I am increasing. So now when I write my intervals out, I know that my increase is taking place from -2 to +2, and my decrease, I actually have 2 of them, are taking place from -infinity to -2 and 4 to +infinity. Not 4, and then 2. Let's see. All right, easy enough? Yeah, can I get some thumbs up or something? All right, thank you, Gio. All right, here's your student practice. I'm going to pause and give you a moment to practice. Points of increase and decrease. What'd you get? Again, you can verbally communicate. You can communicate in the chat. What do we get for increase? What's my interval of increase? Anybody? No? Okay, so we're not awake. So my interval of increase here, I'm increasing from -infinity to 0. And my interval of decrease is from 0 to +infinity. All right, so that's increasing and change. So for your average rate of change, this is what you're using for nonlinear functions. And strangely enough, it just looks like your what? Your slope. It looks like slope still. And so, but it's at a specific time. It's not the entire time. It's not a constant like the linear. It is your average rate of change. So graphs of nonlinear functions are not straight lines. So we have to, that's why we call them average rate of change. And essentially what you're doing is it's the secant line that connects the 2 points that you are looking for that rate of change on. So f of x is my function. This red line, that's my secant. Okay, and essentially I'm just finding the slope of the secant, the slope of the line that connects those 2 points. So yes, it is just a slope formula, yg minus y1 over x2 minus x1. It's just being utilized on nonlinear functions. So here I have f of x equals 2x squared, and I want to find the average rate of change from 1 to x equals 1 to x equals 3. Well, the first thing I have to do is find f of 1, and that gives me 2 times 1 squared, which gives me 2. Second, I'm going to find f of 3. F of 3 is going to give me 2 times 3 squared, and that gives me 18. So then to find my average rate of change, I'm going to do my y2 minus y1 over x2 minus x1. And my y2, I got 18. My y1, I got 2. My x2 was 3. My x1 was 1. So 18 minus 2 gives me, that's not, that gives me 70. I don't know what I just did. I divided it. There. 18 minus 2 is going to give me 16. And then 3 minus 1 gives me 2. And so I end up with questions, comments, or concerns about what we just did. Feeling okay about it? Okay. All right. Thank you, Karen. All right, student practice. So here's yours. I was nice and I did the work for you. So all you have to do is do the calculation. So when we look here and we're doing it, so we're asking for the average rate of change from 1 to 4. And so my x1, my y1, my x2, my y2, and I end up with -3 minus 12 over 4 minus 1. That's going to give me -15 divided by 3, which equals -5 is my average rate of change. Okay, that is average rate of change. So the difference quotient, it's just the slope of the, where are we at? It's where you're finding here as x increases from x to x plus h. So we're finding that distance. So between here, as they're increasing, f increases how much? From f of x to f of x plus h. So the slope of the red line, that's, what do we call that? A secant. That secant line here, we're looking for the average rate of that line. Okay, and then when we go through this process, it simplifies down to the difference quotient of f. So it's basically the average of all of the average slopes on that non-linear function. And this is the difference quotient, f times x plus h. This quotient is very useful in the fundamental theorem of calculus. So here, if I'm finding a difference quotient, I have 3x minus 2. The first thing you're going to do is find x plus h. And that just means that wherever x is, I'm plugging in x plus h. So this is going to become 3 times x plus h minus 2. And that gives me 3x plus 3h minus 2. Okay. After that, now that I have what this is, I'm just going to plug everything in to find the difference quotient. So I know that f of x plus h is 3x plus 3h minus 2, right? And minus my original f of x. So my original f of x is 3x minus 2, all divided by h. And I'm just going to simplify and clean this up. So I have 3x plus 3h minus 2 minus 3x plus 2 all over h. 3x minus 3x cancels out. -2 plus 2 cancels out. And I'm left with 3h divided by h. My h just cancel out, and I'm left with 3. Okay, this is going to always happen with linear equations. That's because your difference quotient is just the slope of the linear equation. So if you do it correctly with a linear, your difference quotient should be the slope of your linear equation. And again, this is foundation for calculus. All right, here's your practice using x squared. Anybody? What'd you get for this quadratic? Nobody? Again, you can write in the chat. You don't have to talk to me. Our party poopers. All right, so we have h squared divided by 2. Okay. Got one answer in. Anyone else? All right, let's see if you got yours right. So we have f of x plus h would equal x plus h squared which equals x squared plus 2xh plus h squared. So that's the first thing you find. And then we're going to plug it all in. So we have x squared plus 2xh plus h squared minus x squared all over h. My x squareds are going to cancel out, and I'm left with 2xh plus h squared all over h. I can factor out an h. So I have h, and I'm left with 2x plus h all over h, and my h cancels out, and I'm just left with 2x plus h. You got a factor here. All right, so that would be the difference quotient for f of x equals x squared. And again, this is foundational for calculus when you start differentiating in that class. So fun, loads of fun. All right, well, if you all have